See? All right.
Hey, you turned it in. What did you just say? We all have great 4.1 now.
Okay, 4.2. Okay, mean value theorem. MVT. All right, mean value theorem. Is this the most valuable theorem? Well, it's important in theory, and there are a few applications, but let's talk about this. Now, actually, before we have the mean value theorem, we have a lemma, I guess, preliminary, Rawls theorem. A special case for this is Rawls theorem, and that's what we actually use to prove this. Okay, so first, we have Rawls theorem, okay, which is an interesting and important theorem all its own, and it's used to prove the MVT. You should know both of these. Okay, so Rawls theorem is a specialization of this, or you could say this is a generalization of that. All right. Rawls theorem, after this for Rawl. All right. Okay, so before we talked about sufficient conditions for absolute extrema, right? That was the EVT. Okay, now the MVT, they basically help us look for critical numbers, guaranteeing the existence of critical numbers. All right. Well, when would that be very helpful? All right. When is F guaranteed to have a critical number? All right. So we're looking for sufficient conditions for a critical number. All right. And that's where we look for things like local extrema. All right. Well, just some basic examples. All right. Okay. Well, it would help a lot if f of a equals f of b. That would help, right? And also, it would help for f to be a nice function in between. And we'll talk about what nice means. All right. So, for example, what would you expect a nice function to do? Okay, you would expect its graph. If it goes up, we expect it to go down. Okay, so if it starts at this point, if graph goes up, graph goes down, we get that point. We expect a nice function to have a graph to look like that. Bear in mind, he might have more adventures. Okay, point here, might be a bit more adventurous. Okay, might have a peak there, maybe a dip there. All right, but still, that's a pretty nice function. Don't you agree? All right. So what are sufficient conditions to have critical numbers? Here you can see that we're going to have 1 over here, right? A critical number is where the derivative is either what or what? 0 or DNE. It's got to be in the domain of Big Daddy F. All right. Over here, it looks like we have how many CNs? Looks like 2, right? 1 over here, 1 over here. Okay. And we could have more. I mean, if we have vertical tangent lines here, then we could have more. Right? I try not to draw it that way, though. Okay. And so we want sufficient conditions for the existence of CNs. I did not say uniqueness. Okay, we could have more than one. Remember, the same thing was true for the IVT. All right, same thing for the EVT. Just because we posit existence, that does not posit uniqueness. We could have more than one. Okay. So, what do we mean by nice? What does Rawls theorem say? And I do have the right to ask you to remember this, write it down, also to apply it. What does Rawls theorem say? And what does it mean to be nice? Okay. First of all, well, we'd like the function to be defined on the closed interval from a to b. That would be nice. All right. Furthermore, we'd like it to be what? Continuous. All right. Well, number 1, if f, I guess I should put if here. If, number 1, f is continuous on the closed interval from a to b. All right. And what's even better than being continuous? If you're differentiable. All right, if you're differentiable. Okay. F is differentiable on the open interval from a to b. Because the thing is, what if this were a half circle, for example, right? Those are exactly the kind of cases where we want to apply Rawls theorem. All right. So we just need differentiability on the open interval, not necessarily the whole closed interval. This is a bit more powerful. It's more general. All right. And, okay, like I said, it would really help a lot, and this is the thing you really have to check, if f of a equals f of b. Yeah, f of a equals f of b. So basically these points are the same height, right? Okay, so the idea is, again, if you have a nice nice graph, right? You have a nice graph, and you're connecting these 2 points. The idea is that you have to turn around somewhere nicely, right? If we assume differentiability, that means we don't have a corner or a cusp, okay? It's got to be kind of a nice point like here or here, okay? Right. And even if you lose differentiability, it may well be interesting, like a corner or a cusp, right? But anyway, those are the conditions for Rawls' theorem. If all 3 of these conditions apply, then what can we conclude? Then, what does that mean? You should remember that logical thing. There exists, all right? There exists a C in the open interval from A to B such that f prime of C equals, well, what has to be true at a critical number? The derivative has to be either 0 or DNE, and this precludes the DNE case, right? We're assuming differentiability on the interior. So specifically, f prime of C would have to be 0. All right. So Rawls' theorem specifically sets up sufficient conditions under which we're going to find critical numbers where the derivative is 0. Okay, you could say those are better critical numbers. They indicate the function's behaving nicer around that critical number. All right. Okay. A couple comments. There could be more than one. Maybe more than one. Okay, like I said, this theorem does not posit uniqueness, just existence, right? We could have more than one critical number where this applies. Okay, maybe more than one. Okay. And again, this corresponds to what kind of tangent line. If the derivative is 0, what kind of tangent line are we talking about? Horizontal, right? And of course, those are interesting tangent lines because the graph might be turning around there. Not necessarily, but it can be turning around there. Okay, so this corresponds to having a horizontal tangent line. Although, if I ask people to state Rawls' theorem, I would like them to write this down as opposed to the geometric interpretation, the graphic interpretation. All right. That's Rawls' theorem. Questions? These are sufficient conditions under which we're going to find a critical number where the derivative is 0. Okay. And we like those critical numbers better, in part because we have more theorems applying to those cases. All right. I want to, yeah.
What happens if, like, condition 1 and 2 are true, but 3 is false?
Okay. So, in fact, that's what the MVT covers. Because I know number 3 seems kind of strong. These 2 seem pretty easy, certainly for polynomials. 3 seems like that's the really strict condition. And, of course, the mean value theorem, when we exclude that, we'll be able to say something much more general. Okay, and that's something you can ask yourselves. How do we generalize this? What if these points aren't at the same height? Okay. Let's start with Rawls' theorem, but we'll extend it over. Any other questions about this? Okay, we're going to remove number 3 in just a moment. Okay, so right now we have very specific conditions, right? We'd have to be very lucky for this to happen just by chance. Okay. Also, my comment here. Well, what if number? Let's see. What if number 2? Again, let's bring this up. On number 2. Why not say the closed interval from A to B? Now bear in mind, the theorem of course would be true if we impose stricter conditions, right? Because this imposes a stricter condition on the function. Okay, so the theorem would still be true, but like I said, this would be too restrictive, and in fact, we'd be restricting whom? I just mentioned these guys. What kinds of graphs have the property that they're nice on the interior, but they fall apart at the endpoints? Half a what? Circle. Half a circle, right. Okay, something like this. That could have been me, actually. Okay, all right, anyway. Okay, something like that, all right? And why do we lose differentiability at the endpoints? What kind of tangent lines do we have here? Yeah, vertical, right? So we lose differentiability at the endpoints, okay? And yet, you would think that, you know, these semicircles, these are exactly the kind of cases where you think Rawls' theorem would apply, because of course we still have a horizontal tangent line in there. All right, so that's the key reason why we made that open and not closed, okay? Why we don't just say differentiable up here, for example, because we want to include the half circle, certainly, right? Those are like the most basic cases where So the most basic case is where you have a horizontal tangent. Okay. So the thing is, if we can make the conditions more general, and still the conclusions are very easy to state, like so, then you go ahead. Let's be a little bit more liberal. We can make this more open to more functions, okay, more possibilities. It makes the theorem more general. When possible, as long as it doesn't make it a lot more complicated, we try to make these theorems as general as possible. Okay, so if that means that we make this open instead of just closed, fine. Okay, so it's a bit more liberal. It can allow for things like half circles. Questions? Questions? Alright. Okay, let's do an example. Alright, example. See, consider the following function rule. F of x equals, what? X to the fourth minus 18x squared, okay, on the closed interval from -4 to 4. Okay, remember, we're treating this as a restricted domain. We don't care about anything that happens outside of that restricted domain. Okay, so we're considering the behavior of this function on this closed interval. So first of all, we have to check to make sure that Rawls' theorem applies. All right. Okay, Rawls' theorem doesn't apply. Okay, so let's just sort of check these off. Well, just by virtue of the fact that this is a polynomial, because f is a polynomial function, then 1 and 2 check off automatically. Because f is polynomial. He's polynomial on this nice closed interval domain here. All right. So we have continuity, we have differentiability, even with the brackets here. All right. Remember, a polynomial graph never has vertical tangent lines. Right? A polynomial graph never has vertical tangent lines. We love polynomials. Now, this is the part that we really should verify. Number 3, does f of a equal f of b? Of course, a here is -4, b here is +4. We still assume a is less than b here. Okay, so let's check this out. All right, and there are 2 ways we can do this. All right, let's check condition number 3 to make sure Rawls' theorem applies. This is the hardest one, right? Okay, well, we can do it directly, right? We try f of -4. All right, we plug in -4 for x up in Big Daddy, right? That's going to be -4 all to the fourth minus 18 times 4 squared. What, -4 squared? Minus 18 times the square of -4, and that's going to be -32. All right. Let's also check f of what? +4. Now, if you do this, you're also going to get -32. Okay. So that checks number 3, right? We know that f of -4 equals f of 4 because these are equal to each other. Actually, it turns out that I didn't even have to work out these calculations. I can just make a single observation about f. Very simply, what kind of function is f? F is even. F is even. Okay? And because f is polynomial, right, it means that these guys are in the domain, right? There's no blowing up or anything. Okay? F is even. We know that f of -4 equals f of 4. Okay? That checks out. Right? So you can either explicitly verify that the function values are equal, or just observe, hey, this function's even. Right? And by the way, this is a category of cases where you would expect f of a to equal f of b. If you have an even function, and if a and b are opposites. Right? Okay, then you're guaranteed that this relationship will hold. Although you can apply Rawls' theorem in other cases, but in the case where the function is even, then you're not relying as much on mere coincidence. Right? But any questions? Any questions? Okay, fast way to check number 3. Therefore, Rawls' theorem does apply. Yes, it does. Okay, the conditions hold. If the conditions hold true, that means that the conclusion must also hold true. All right. So by Rawls' theorem, since we know the conditions apply, remember you only have the right to apply a theorem if the conditions apply, right? We verify they do. Okay. By Rawls' theorem, there exists some value c in the open interval from -4 to 4, such that the derivative there is what number? 0. Okay? We're guaranteeing the existence of a horizontal tangent line somewhere in there, and in fact there could be more than one place. Yeah. So there does exist a value c in there. All right? That's what Rawls' theorem says. What's a natural follow-up question? Yeah, find all values of c in that interval. That will work. Where is the derivative equal to 0? Any questions so far, though? We know that there's at least one place, right? There's at least one place where we get a 0 derivative. There could be more. Any questions? You believe there's at least one. Okay, so find such c. Okay, we know there's at least one. There could be more than one. All right. Now let's remind ourselves what f of x is. F of x equals, what is it? It's x to the 4th minus e to the x squared. All right. So let's find the derivative. And you can use either f prime of x or f prime of c. It doesn't matter. I'll just say f prime of x. All right. Well, what's the derivative? 4x cubed minus 36x squared. All right. X. All right. 4x cubed minus 36x. Remember, the derivative of an even function is odd, by the way. All right. And I want to set this equal to, yeah.
When you say that there's at least one, are you referring to the vertex? Because it's
Well, for a parabola, it could be. It doesn't have to, though. Now, bear in mind, this is a 4th degree guy, right? So he could have 1 or 3 turning points.
It would depend on the range. I mean, the domain.
Well, to me, it's all reals.
No, I mean, like if your domain didn't include the vertex, I mean the interval.
Well, I mean, the interval, the restricted interval.
That's right.
Yeah. Now, bear in mind, technically, he doesn't have a vertex, he's a quartic. But, well, we'll see. Remember, a 4th degree guy can be a bit more complicated, right? Yeah. But yeah, he's right that if you have a parabola, like quadratic, then it depends if the x-coordinate for the vertex h is in the interval. And I suspect it would be, because how else would f of a or f of b? The vertex would have to be in there somewhere.
Number 2, is it different?
Differentiable. I didn't want to write it. Differentiable. Okay, meaning there's a derivative at every number in there. Okay. All right. We want to set this equal to 0. We want to find out what this guy is 0 on this interval. Technically an open interval. Right? It's an open interval because remember there's no two-sided derivative at an endpoint in this setting. All right. So solve. F prime of x equals 0. All right. So 4x cubed minus 36x equals 0. All right. I suggest factoring. I think it's very dangerous to divide by x. Let's factor. All right. We factor out of 4x. We get x squared minus 9 over here. All right. After this, we have 4x. Factors as x. X plus 3. X minus 3. All right. Now, it turns out that there are 3 zeros here. All right. Let's check them out. Okay, so my proposed values for c equals 0, or, should I say and, 0 and negative 3 and positive 3, or, maybe or. Okay. C could be 0 or negative 3 or positive 3. I have to ask the question, are these all in the interval? Well, are they all in the interval here? Yes, they are. Okay, so double checking, they are all in the open interval from -4 to 4. Okay. Technically, if you get an endpoint, we should show it because remember, you can't have a two-sided derivative at an endpoint in this setting. So we take all of them. All right. So yeah, we actually have 3 places where we have a horizontal tangent line, and it's not so surprising that these are symmetric about 0 because we have that. Remember, we have that symmetry, right? The graph of Big Daddy F is symmetric about the y-axis. It's not so surprising that we have that symmetry. Questions? That's what you have to do. Questions?
If I want to include this one, same question.
Well, what we're doing is, this says that by Rawls' theorem, there will be at least one value in here where the derivative is 0. Here, we're finding the values of C where the derivative is 0. It's a natural follow-up question. Okay? Now, folks, you have to have at least one number in here in the interval, otherwise you did it wrong, because Rawls' theorem says there's got to be at least one. Here we happen to have 3. Okay, well,
The example initially has a closed interval, but now it seems like it's an open interval.
yeah, because again, as far as we're concerned, the closed interval is the restricted domain, and we don't have a two-sided derivative at the endpoint of the restricted domain.
So
That's the reason.
if the critical points were like -4 or 4 or 0,
We would
eliminate.
we would technically kill the -4 and 4 because we wouldn't have a two-sided derivative. Remember, a derivative by definition is two-sided, unless we say specifically it's one-sided. Bear in mind, on an exam, I'm not going to harass you about that issue on the exam. So if you were to box a guy like that in, I may very well not even bother taking it off. but still, technically, yeah, we would kill him.
Yeah, I was just going to ask if you can do any kind of validation or verification.
I'm going to grab it.
You are.
Okay, yeah. So in fact, one skill you're going to learn later in the chapter, something to look forward to, is that you're going to be able to graph these guys, these kinds of cortex. All right. Okay. Well, let me show you what it looks like. Well, we know that these 2 points lie there, right? -32. Okay, the graph's going to look like this. All right, x, y. All right. And it's going to be different scales, of course. All right. So at -4 and +4, okay, we know that -32 is there. Here. Oh, no, I'm sorry. Oh, no, okay, over here, all right. Okay, and at -3, okay, what's going to happen is, it turns out the graph is going down. Okay, so we have a horizontal line here. Goes up towards the origin. Bear in mind, f of 0 is 0, so we look at the origin. By the way, f is what kind of function? Even, right? So it's going to be symmetric. There's +3. Going to go down all the way here. Okay, and you can find out where this y coordinate is. We plug in either 3 or -3 into whom? You get the y coordinate? Big Daddy. Big Daddy get the y coordinate. You can find out who it is. All right. And then we go back up here. All right. Okay. Now, by the way, if I were to go on, okay, remember overall this was like an upward opening bowl in the long run. So if I were to go on, it would look like a big W, right? Any questions? Any questions? And then, by the way, don't forget, over here, also, we have a horizontal tangent line. Remember, there are 3 places here where we have a horizontal tangent line. At x equals -3, x equals 0, and x equals +3. And it turns out that all 3 of the corresponding points are turning points. Bear in mind, they're not always turning points, right? Okay, but in this case, all 3 points are turning points. Okay. Questions? By the way, this whole thing with Rawls' theorem, it's kind of like, imagine 2 people holding 2 ends of a jump rope. Remember jump rope from way back in kindergarten, right? So you have one person here, and they're wiggling it, right? So they keep wiggling it, and it doesn't break or anything, right? Then you should be getting some places with horizontal tangent lines, right? Even if they hold it straight, right? You have a bunch of horizontal tangent lines. If they wiggle it, right, then you're going to get at least 1 horizontal tangent line. So we have 3. And these guys are symmetric because of the symmetry along the y-axis. Okay. Any questions? Rawls' theorem guarantees the existence of a critical number in the interior where the derivative is specifically 0. And that helps with the mean value theorem. Rawls' theorem is used to help prove the mean value theorem. Okay. And helps out that 0 derivative. Okay, some of you might be going, well, why not D&E? Well, because we need Rawls' theorem to prove the MVT. And the MVT does require 0 specifically. Alright. Okay, going on. Going on to what Paul was saying, what if we kill condition 3? Because that seems too strict, right? F of A equals F of B. That's very strict. What if we remove it? Let's relax that condition. Alright. Issue B. What is the MVT in general? Again, the mean value theorem for derivatives, there's one for intervals, but the mean value theorem for derivatives, maybe I should even mention that, for derivatives, you want to be super precise. Again, there will be one for integrals in chapter 5. The MVT for derivatives is a generalization of Rawls' theorem. What happens if we relax condition 3? All right. Now, before I write down the theorem, I'm going to do a basic application. So in case you're wondering what the practical value of this is, okay, here's an example. All right. My favorite example from the movie Speed, right, with the late great Dennis Hopper, right, as the villain. So let's say I'm the late great Dennis Hopper, and I'm talking with Keanu, all right, and I tell Keanu, all right, hotshot, here's the deal. You're on this bus, okay, and you're going to go up to 5. You're going to go up north on this big old highway or whatever, right? Okay. So here's the deal. We're going to clear the freeway. At least it's cleared off. Okay. Now, your task is that you have to go exactly 100 miles due north in exactly 2 hours. You have to do that. Okay. So a car or bus. A bus goes due north. Okay. So there's no confusion. Okay. Goes due north. Okay. Well, 100 miles in 2 hours. Okay, when I say that, I mean exactly 100 miles in exactly 2 hours. It's got to be on the dot. A bus has to go due north 100 miles in 2 hours. Exactly. All right, now, if I were to graph a position function, all right, so y equals s of t. S here is a position function. All right. Let's assume that s of 0 is 0. So when Dennis Hopper calls Keanu, we're going to say, okay, that's the 0 point. That's where we're starting. Okay, s of 0 is 0. So this point has to be on the s graph. Now, in exactly 2 hours, Keanu has to be exactly 100 miles up. Okay. So if we're graphing against the time axis in hours, okay, this is miles. Okay, that means that when t is 2, okay, different scale, then s of 2 has to be 100 in miles. So the graph of s has to hit that point. Now, here's the condition. Dennis says, all right, hotshot, here's the problem. Now there are no gaps in the road, okay, no Back to the Future tricks, no gaps in the road, okay, no turbo rockets on your bus. There's a bomb on the bus. It goes off if the bus ever hits 50 miles per hour. How should Keanu feel? Horribly, because there's no way you can avoid that. Okay. Let's talk about why. What is 50 miles per hour? Okay. Now, whatever strategy, if you can imagine Keanu strategizing, but you know, however Keanu does this, right? Okay, whether he starts off slowly and then speeds up. Okay. Now remember the slopes here. The derivative is the what? What's the derivative of position with respect to time? Velocity. Okay, the slopes are velocity. So Keanu might start off slowly and then get faster. Maybe he starts off fast, then goes more slowly, or he just decides to go to constant speed, in which case, boom, right here, right? But regardless, the slope of the secant line, right? Whatever his strategy, the slope of the secant line is going to be the slope of this guy here. And guess what the slope of that secant line is? It's 50 miles per hour. What is that? That's the average rate of change. That's pre-calc, right? From pre-calc, the average velocity, the average rate of change here is the slope of this secant line, right? It's the slope of the secant line connecting these two endpoints. It's going to be 100 miles over 2 hours, 50 miles per hour. Okay? So you agree that however Keanu strategizes, okay, his average velocity over the entire trip is going to have to be 50 miles per hour. What the MVT for derivatives says is that at some time in there, the instantaneous velocity has to hit the average velocity. So however you strategize, whether you start by going slowly and then faster, or going fast and then slow, however you cut it, at some time in there, you're going to hit 50 miles per hour. Okay? Now let's get less macabre. Let's say that the bomb is a dud, okay, so that, you know, in fact we do get the complete graph. Okay? So let's assume the bomb's a dud, alright? So we do get the complete graph. Alright. How will we cut it? Right? At some time between 0 and 2 hours, like, you know, noon to 2 p.m., whatever. Let's say Dennis calls it noon, right? Sometime between noon and 2 p.m., the bus has to hit 50 miles per hour. Okay? So at some time in there, what the MVT is going to say, now I realize that I have not yet formally introduced the MVT yet, but what the MVT concludes is that there exists a time t in the open interval from 0 to 2 in hours when, okay, the derivative there, okay, s prime of t, which is the instantaneous velocity, okay, s prime of t is v of t, the instantaneous velocity v of t, all right, s prime of t is v of t. With s prime of t, the instantaneous velocity equals the what velocity? What's the pre-calc idea? The average velocity. If we're going to talk about average velocity, we have to specify the interval. Well, the average velocity on the closed interval from 0 to 2, from A to B. All right. And from this, we can generalize this, and we can intuit what the mean value theorem for derivatives will say in general. Okay. But you all buy this idea that at some time in here, the bus is going to have to hit 50 miles per hour. Right? In order to accomplish this task, the bus has to hit 50 miles per hour sometime in there, maybe more than once. Okay? So if you all buy that principle, then you all should buy what the MVT here is. And what does the MVT say? All right. The mean value theorem for derivatives. Okay. Again, in chapter 5, we'll have one for intervals. And like I said before, these are important for proofs in calculus. Later on, we're going to see the fundamental theorem of calculus, and this is used to prove that. He's like the man behind the curtain, like Oz, right? The man behind the curtain, Wizard of Oz. Although there are some practical applications directly. Right? Really, what the mean value theorems are going to do, they're going to really form the bridge between pre-calc and calc. I mean, this notion, right? The idea that you have to hit the instantaneous velocity, the idea that the instantaneous velocity has to equal the average velocity somewhere in there, that's a bridge between calculus and pre-calculus, right? The idea between instantaneous and average. Okay, at some point they have to match up. Okay, and that's a key bridge between pre-calc and calc. That's how you go from pre-calc ideas to calculus, formally. So these guys are important in proofs. Now, what does the MVT say? If, you know what, the first two conditions are the same as for raw, and like Paul's bringing up, the only thing we're going to do is we're going to remove condition 3. We're going to relax that condition. All right, so if number 1, what were our niceness conditions? If a function f is defined and what? Continuous. Continuous implies defined, right? If f is continuous on the closed interval from A to B, remember, we're implying throughout that A is less than B, of course. All right. Otherwise, that's the empty set. Or just one number. Okay, so if f is continuous on that closed interval from A to B, all right, and number 2, f is what makes f even nicer. If it's differentiable. So remember, first you're defined, then you're continuous, then you're differentiable. Okay. F is differentiable on, we just need it to be differentiable on the open interval. Remember, we're going to tolerate things like vertical tangent lines at the endpoints. Okay. Maybe not VAs, right? V continuity. Maybe not VAs. We can tolerate things like vertical tangent lines or something. Right? F is differentiable on the open interval. Then, okay, we're removing condition 3, because that was very strict, right? F of A equals F of B. You can see here that the 2 points here are not at the same height, so Wall's theorem doesn't apply, not directly. All right. Then, okay, what's our conclusion? Then, there exists, it's an existence theorem, just like the Wall, just like the EVT, just like the IVT. Right? Okay. Then, there exists a value C in the open interval from A to B. Okay, this means there exists a C in the open interval from A to B. All right, maybe more than one. Such that, okay, I'll write this out with braces at first. Such that the instantaneous rate of change there at C equals the average rate of change on the interval from A to B. Remember, an average rate of change requires an interval that it's averaging over. All right? So if I ask you for the mean value theorem, and I have in the past, then you better be able to write this using mathematical notation. Don't just write it out in words, write it using mathematical notation. So there exists a C in here such that, okay, remember f is the big daddy function, not s here. F is the big daddy function. How can you describe, using notation, how do you denote the instantaneous rate of change at C? Very simply. What is it? What is it? What's that D word? It's a derivative. What's the notation here? F prime of C, right? This represents the instantaneous rate of change at C. It's the derivative of f at C. In the context of a position function, you're talking velocity. Right? Okay, so here it's f prime of C equals, you should remember this from earlier in the chapter, it's a difference quotient, right? That's pre-calculus. What's the average rate of change? It's pre-calc. Rise over run, folks. F of B minus f of A all over B minus A. That's called a difference quotient. Remember that? That's section 3.1. If you forgot this, shame on you. Look back at 3.1. Okay. The difference quotient, that gives you the average rate of change of f on that interval. Okay, rise over run, f of B minus f of A over B minus A. Right? y2 minus y1 over x2 minus x1. Right? Rise over run. Okay. Question. Again, C might not be unique, right? There could be more than one such value for C. Okay. Any questions about that? Any questions?
Is there any reason why you couldn't write that as the other formula using H?
Well, H is B minus A. And we're not taking a limit here.
Oh, that's good.
So, yeah, this is average. And H is specifically B minus A. Okay, so if you want to state it, you should say B minus A. You could put H there, but then you have to write on the side. By the way, H is B minus A. Okay. Questions? Questions? Now, what if f of A is f of B? Okay. What if f of A equals f of B? All right. So the picture looks like this, maybe. Okay, here's A, here's B. F of A equals f of B. Then we're looking for a value for C, blah blah blah, where f prime of C is what number? If these are equal, then what number are we talking about here? 0. Does that sound familiar? Whose theorem is that? Rawls' theorem. Yeah. That's Rawls' theorem. So this demonstrates that Rawls' theorem is merely a special case of the mean value theorem. Okay. So Rawls is a special case of all this. Which makes sense because we use Rawls to prove them in the first place. Right? Okay. Yeah.
If B and A are the
Anything else? Any questions? By the way, how does the picture extend? How does the picture extend? All right. So over here, what do we say? All right. However the graph goes, right? Remember, it's got to be a nice graph, right? You can't have any funky VAs or anything in the middle, right? Okay. What Rawls' theorem is saying is that if f of A equals f of B, you have to have what kinds of tangent lines in the interior? At least one horizontal tangent line. Okay. Now, how does that extend to the MVT? Well, what does the secant line look like here? What is the average rate of change of f here? Look at this. What's the slope of that line? 0. Okay. The average rate of change is 0. Okay. In this case, it's like the car is going north and south. Okay. Remember, velocity is negative if you're going in the wrong direction, right? So, and that's possible. Your average velocity could be 0. Maybe not your average speed, but your average velocity could be 0. That means when you're going north, the velocity is positive. When you're going south, the velocity is negative. You're getting a perfect balance. Basically, you end up at the same point you started. Okay. Now, how does that extend to the mean value theorem? It's almost like you're tilting the picture. All right. So, at the MVT, what's happening here? I'll go to X and Y. So let's say that, here's A, f of A, and here's B, f of B, okay? Well, the idea is, let's say you have a graph looks like this, for example, all right? It's a nice graph, right? No funky behaviors in there, all right? Here's the secant. Once again, the average rate of change of the function on that interval is the what of that yellow line segment? It's the slope, right? Whatever, it was 50 miles per hour in the speed example, all right? Now, what am I claiming here? There are places in here where the tangent line is not necessarily horizontal, but is what? What's that P word? Yeah, slopes are equal. What do you call lines with equal slopes? Parallel. Okay, like maybe here, for example, here, looks like there are a couple places, right? So this is like C1, that's C2, right? So the mean value theorem posits the existence of tangent lines that are parallel, at least one tangent line in there, in the interior, that's parallel to the secant line. And why is that interesting? It's a place where the instantaneous rate of change equals the average rate of change. And why does calculus care? Because that's a bridge. That's how you use the mean value theorem in proofs, because it bridges from pre-calc to calculus. All right. There's a guy in here that matches up with the average rate of change. There's an instantaneous rate of change here that matches up with the average rate of change. And calculus likes that. Proofs like that. Okay. All right. Let's do an example. All right. Consider f of x equals x to the fourth minus x. This guy is neither even nor odd, by the way, on the closed interval from 2 to 5. Okay. Now, Rawls' theorem has nothing to do with this guy, right? I mean, okay. So Rawls' theorem does not apply here, as it turns out. That's okay. The MVT will, because this guy's a polynomial. We love polynomial functions. All right. Well, because 1 and 2 check out, trivially, the mean value theorem applies. Okay, that's trivial because, of course, we have continuity and differentiability. Right? The MVT applies automatically. Okay, bottom line, because f is polynomial, although on a restricted domain, but he is polynomial. Right? Okay, so the MVT applies. All right. So what does that mean? Because the MVT applies, that means that there exists some value c, maybe more than one, in set membership, in the open interval from 2 to 5. If you put closed brackets, I won't be deeply offended, but open brackets, open parentheses. There exists a c in the open interval from 2 to 5 because we have two-sided derivatives in there. Right? Remember, we're requiring differentiability on the open interval, not the closed. All right, kind of zoom. Okay, such that. Okay, so what do we need such that f prime at c equals, that's a difference quotient. Okay, f of 5 minus f of 2 all over 5 minus 2. All right, I trust you can work that out. Okay, by the magic of calculators, we find that that's 202. 202, not 0. A very common error in these problems, you're so used to saying derivatives equal to 0. Here, you don't set equal to 0. You set equal to 202. So please, not 0. That's like an automatic thing we tend to do. Here we do not set equal to 0. All right, that's not what we're looking for here. Well, that's what the mean value theorem says. What do you
I'm sorry. So basically, we could have a critical number where the secant line. We could look for critical numbers.
No. This is not a means to find critical numbers. This has nothing to do. Well, it has nothing to do directly with critical numbers. It has to do with relating instantaneous rates of change with average rates of change. Again, we care in calculus proofs because this is the bridge between pre-calc and calc. We're relating instantaneous rates of change with average rates of change. That's key for proofs. That's the bridge from pre-calc to calc. It has nothing to do with critical numbers.
Since there's a bracket 2 and 5.
That's okay. Well, again, these are open parentheses because, again, and we do not have two-sided derivatives at endpoints of this interval.
In that graph, could we call C1 and C2 critical points?
No, they're not. So this is like our example here, the slopes would be 202. Right. Whatever the slope of the secant line is from here to here, that's what we're looking for. That's slope. Okay. It has nothing to do with critical numbers beyond the fact that Rawls' theorem is used as part of the proof.
So Rawls' theorem finds the average rate of change?
Well, part of the calculation here is if I give you a function and an interval, then you should be able to find what slope we're looking for specifically, right? Because you work out the difference quotient. Right. Now, if I ask you for the mean value theorem in general, just give me the general notation. But if I'm giving you a specific function rule and a specific interval, you can work out specifically what slope we're looking for. What is the rate of change we're looking for? Right. So where in the interior is the average rate of change 202, or whatever the unit is? Anything else before we calculate? Okay. Well, because what is the natural follow-up question? What's the follow-up? Yeah. What is or are appropriate values for C? Yeah. Find all such C. You know there has to be at least one. Okay. Has to be at least one. Find all such C. In fact, if you just have the secant line as the graph, you have infinitely many values for C that will work. All right. But find all such C. All right. To do that, what do we have to solve? We have to solve, okay, f prime of, you can say x, that's fine. F prime of x equals 202. I don't care if you call it x or c at this point. Okay, but basically we want to know where the derivative is 202. I don't care if you use x or c. All right. Now, f of x is this guy. You should be able to give me the derivative. What's the derivative of x to the fourth minus x? 4x cubed minus 1. Don't forget the minus 1. Okay, equals 202. All right. You're very lucky because it's very easy to isolate the cube. Otherwise, you might have to use stuff like rational zero tests, right? Synthetic division. I could have done that, right? For a general cubic, have a bunch of terms there. Use the rational zero test, the rational roots theorem, right? The P over Q thing, plus minus P over Q. Synthetic division, that's fair. This is easy. Isolate the cube. 4x cubed is 203. Add 1, right? Divided by 4. X cubed is 203 over 4. So I want x to be the what of that number? Cube root. Plus or minus? No. For cube roots, not plus or minus. Anyway, I wouldn't want the minus 1 anyway, right? All right, so x equals the cube root of 203 over 4. Instead of rationalizing the denominator, let's just approximate this. It's going to be about 3.702. So C, the number we're looking for, right, is about 3.702 to 4 sig figs. I'll tell you how far to round off on the test. Now, this better be in the interval because it's an existence theorem. You agree it is? Yeah. Right? Yes, it is. Okay, so verify yes, it is in the interval. It better be. If that's not in there, then you messed up somewhere. Okay, either the MVT didn't apply or you messed up a calculation. This number better be in here, all right? And that's our answer. Graphically, what does this look like? Okay, well, I just need the piece of that between 2 and 5. That just looks like a J. It's not all that interesting. It looks like a J. All right, so if you graph this, turns out the graph looks like this. X, Y. Between 2 and 5 looks like a J. All right. This here's 1,000, by the way, way up here. Okay, so we're talking different scales here. Okay. Now, if you look at the secant line, hey, we calculated it. What's the slope of that yellow secant line? What's the slope? 202. Some of you might be thinking, and I remember in high school when this whole concept confused me, some of you might be thinking, oh, that looks like a slope of 1. What do you mean 202? Well, yeah, but why is the slope not 1? Yeah, look at the scales. Yeah, if you have different scales, it's going to mess up your visual sense of slope. Remember that in Calc 3, by the way. Because in Calc 3, for example, in Calc 3, you know, if you're using different scales, right, that's a square, and these are perpendicular, right? Okay, so, you know, so be careful that your eyes might deceive you if you're using different scales. not to say that you won't be doing this fairly routinely using different scales, but just be aware that sometimes these are going to be squares and these are going to be perpendicular. Right? So watch out for those relationships. Okay. Anyway, we're looking for parallel tangent lines. Bear in mind your visual sense of parallelism, it doesn't make sense here. Okay, it looks like the lines point in the same direction. Okay, this would be 3.702. About. Okay, so yeah, these lines will be parallel. Okay, and your eye is good at that even with different scales. For perpendicularity, no though. All right. All right. Questions. Now, example. F of x equals 1 over x minus 5 on the closed interval from 4 to 6. Will the MVT apply? Will the MVT apply?
No.
No. Yeah. This guy's messed up where? 5, yeah. So this guy's no good. In particular, f is discontinuous, and x equals 5. Now, if the interval went from like 10 to 20, then it wouldn't be a problem. But this one, that interval includes 5, so we're dead. That means the MVT does not apply. Okay. And because this guy really gets messed up at 5, the whole concept of a secant line loses meaning. Okay. But let's investigate this further. All right. So, well, actually, I should go. X-axis, y-axis. All right. So here's x equals 5. All right. Here's 4. Here's 6. All right. And then, okay. So we have one piece going like this, going like that. Another piece going like this. All right. This is symmetric about that point. Okay. So that's the graph of f on that interval. Okay. Now, if you look at this secant line segment here, all right. First of all, because this guy's so messed up at 5, this guy may not have any good meaning, quite frankly. Okay. And for that matter, even though, okay, now the MVT doesn't apply, well, we could still have parallel tangents, but are there going to be any parallel tangents for that guy? Well, this guy has a positive slope, right? What are all these slopes? Draw what? Draw negative. Okay, so you're not going to get such a C. No such C exists. Okay. Bear in mind, you might have, it's possible that there might be such a C where f prime is the difference quotient. But again, the whole idea of average rate of change might fall apart here because this guy totally gets messed up at 5. Okay, although books don't formally state it, when we're talking about average rate of change, the assumption is that the function does not totally freak out somewhere like it does over here at 5. Okay. All right. So sometimes the MVT doesn't apply, and sometimes you don't get a parallel tangent. That happens.
Yeah, first sign is obviously that the slope is negative and the thing is from positive.
You mean this guy?
Yeah.
Well, this is an example where the MVT doesn't apply. There is no value of C, where the tangent line is parallel to the secant line. But see, if the mean value theorem doesn't apply, we had no guarantee of a parallel tangent. Okay, so it's all messed up here. I just want to show you a case where the MVT doesn't apply. Okay. Here, very severely so because of that VA, which means that the secant line really loses value in terms of interpretation. I mean, what's the meaning of that? We don't like talking about average rate of change when you have this kind of violent behavior right now anyway. All right. Now, some of you might be going, well, wait a minute, this whole idea of A and B, where are these things coming from? Let me tell you an interesting corollary of all this, an interesting result. Let's say you have a function that's differentiable everywhere. Okay, let's say you have a function f that is differentiable on all the reals. Okay, give me a category of functions that's differentiable everywhere. Starts with P. Yeah, polynomial functions, right? Take any polynomial function, for example, right? X-axis, I don't care what the y-axis is. In fact, I don't care what the x-axis is either. But let's say you have a graph. I'll put it in a y-axis. Okay, so let's say that you have some polynomial graph, whatever it looks like this maybe. Okay, and you can play with this on a napkin. You know, you're watching TV tonight. It's a commercial break, right? Okay. Take any two values a and b. Take any 2 points on the graph. Actually, take any 2 distinct points on the graph. Maybe this point here and this point here. All right. You can call this guy's x-coordinate a. Call this guy's x-coordinate b. We assume a is less than b. Draw the secant line connecting the 2 distinct points. Okay. What does the MVT say? Somewhere in the interior, you will find a what?
Horizontal.
Well, not necessarily horizontal, but a parallel tangent line. A parallel tangent line. Okay. Bear in mind, the graph could well be the secant line itself, right? So, in which case, this guy here would have there'd be no critical numbers. There'd be no turning points here. Okay. But here, it looks like there are 3 values for c where the tangent line is parallel to the secant line. So here it turns out there are 3 values of c that will work, apparently. And then to figure it out, you can figure out what f is and work out the work that we did before. Okay. Any questions about that? Any questions? Before we take a break, I'm going to take 3 minutes to explain how you prove the MVT using Rawls' theorem. This will take me 3 minutes. If you don't get this, don't worry about it. But I think it's cool. It is kind of cool if you understand the gist. So in 3 minutes, how is Rawls' theorem used to prove the MVT? Very quickly. And if you don't get this, don't freak out. All right. Let's say we have a nice polynomial function f. All right. Here's a, and here's b. All right. Here's a secant line that connects the points. All right. Now, I'm going to call the corresponding linear function for the secant line g. All right. Now, wait a minute. I thought Rawls' theorem was applied to a guy where the function values of a and b are equal. That's not true for f here. It's not true for g. But you know what that is true for? This gap. Let h be f minus g. That represents the h function. What's h of a? What is f of a minus g of a? What's the gap here? H of a is what? What's the gap? What number? There's no gap. What number? 0. H of a is 0. What's h of b? Again, we're meaning 0. So look at this. H of a is 0. H of b is 0. We assume f is nice. Of course, g is nice. Therefore, h is nice. By nice, I mean, continuous, blah, blah, differentiable, blah, blah. Okay, h is nice. You know what I mean. Continuous on the closed interval, differentiable on the open interval. All right. So, who applies? Rawls' theorem applies to h. Rawls' theorem applies to h. Okay. What does the graph for h look like? The graph for h looks like this. Okay, here's a, here's b. H of a is 0, h of b is 0. Might look something like this. All right. What does Rawls' theorem say? There's at least one value for c where we have the derivative being 0, horizontal tangent line. All right. Guess what? This value of c corresponds to this value of c, where the tangent line is parallel. Why do they correspond? When does h prime of c equal 0? All right. Okay, h is f minus g. All right. The derivative of a difference is the difference of derivatives. That means that f prime of c minus g prime of c equals 0. Add g prime of c to both sides. F prime of c is g prime of c. These are equivalent. So that h prime function is 0 exactly when the slopes are equal along the f graph and the g graph. And that's why the MVT works. If you didn't get that, don't worry about it. I'll see you in 10 minutes.